And then yesterday we had discussions on converters for energy storage, specifically with the SIC based systems. So during these 3 days, we had different aspects of energy storage, which is being used for different applications. And today we will be having a battery management system for electric vehicles, specifically for electric vehicles, by Dr. R. Kalpana from NIT Surathkal. She was engaged somewhere in the meetings with his management, and that's why she's not able to join by now. So what I was thinking that all the participants, if they can have some kind of feedback or discussions, because there may be many queries, or you can say uh, some basic questions, because many of the students or many of the participants maybe are not aware of all these things what have been discussed in last 3 days, like phase lock loops and SIC based systems, converters, bidirectional, or there was a dual active bridge converter. So, if you are having that kind of query, till our expert joins, we can have the discussion. So any participant, if he is willing to have any query, we can have those discussions. Anyone? Okay, how many participants are getting whatever we have discussed during these 3 days? Phase lock loops, how many have understood or whether they were aware of phase lock loops or not? Okay, one participant has raised hand that she was aware of phase lock loops. Anyone else? What about dual active bridge? Yesterday and even on the first day, Dr. Ajish Gupta discussed about dual active bridge, DAB converter. Because these are the things which are taking up they have taken up recently in energy storage, or these bidirectional converter, bidirectional energy flow. Many things are there. Then the third one is today's topic, battery management system. Okay, let us see if we are having a battery for a high voltage operation or for a low voltage operation. Suppose you are having a battery, all may be aware that it is in the multiples of 12 volts. Usually this is the standard. So we have a 12-volt battery, and we manage it in the multiples of 12. So 12, 24, 36, 48. So usually we have 24-volt battery, 12, 24, or then 48-volt battery, and 72, like that. So whenever we are going for higher voltage, okay, our guest has joined, I think. Dr. Kalpana,
Yes, sir. Yes,
welcome.
yes.
Yeah, good
Yeah.
evening.
Good evening, sir. Sorry, I'm a little bit late. There was some other issue in our institute, so we had a meeting with the
Yeah, yeah.
director.
I can understand that sometimes it becomes really very critical. So, not an issue. So, on behalf of MANIT Bhopal and the organizing team of this faculty development program on innovation and challenges of energy storage technologies, I welcome Dr. R. Kalpana, is associate professor in NIT Surathkal, and she will be discussing about the battery management system for EVs. Dr. Shailendra, I request you to kindly introduce the guest.
Yeah, sure, sir. So, am I audible?
Yes, you are audible.
Okay. So, Dr. R. Kalpana received a BE degree in Electrical and Electronics Engineering from Madras University, Chennai, Tamil Nadu, India in 1998. ME degree from Anna University, Chennai, Tamil Nadu, India in 2000. And PhD degree from Indian Institute of Technology, Delhi, India in 2000. Presently, working as assistant professor at Department of Electrical and Electronics Engineering, National Institute of Technology, Karnataka, Surathkal, India. He has 10 years of teaching since 2018 and the corporate member of the Institution of Engineers, India. He has publications more than 20 in IEEE journals and 50 national and international conferences and filed 4 Indian patents. Her field of interest are improved power quality converters, renewable energy systems, and battery management systems for electric vehicles. She guided 2 PhD students and more than 15 UGPG students. She received DST SCRB grant worth 22 lakhs and presently working on DRDO NRB project titled Theoretical Analysis and Design of High Efficiency Wideband Class D Amplifier for Acoustic Transducer. She has taught more than 10 courses for UG/PG students and developed a laboratory course on power electronics design. She has continuously involved in various department and institute level activities. With this, not taking much time, I would like to invite ma'am. Uh,
Thanks for the introduction. And, my video is not working, so I'll share the
no,
slides.
Yes, yes, please share the slides. Shailendra, have you given sharing rights?
yes. Madam, are you able to?
Do you, madam, do you get
No,
the share?
no, sir. I'm not able to. That is
Share.
not sharing is
Yeah,
not there.
Shailendra, you give her owner right.
There is option at the top like share content. Share content. Control 50.
Here, here. So that option is not highlighted. Share and sharing option.
शैलेंद्र,
Yes, sir.
आप ना और
Yes, sir.
मतलब उसमें ओनर वाले राइट्स में आप इनको कर दो।
Yes.
एक्चुअली
सर एक्चुअली
गेस्ट वाले
ओनर
में
राइट्स में तो वही आ सकता है जो टीम में ऑलरेडी अपनी अवेलेबल हो सर।
नहीं, तो अभी 2 दिन से बाकी लोगों के साथ कैसे चल रहा था?
वो तो ऐसे ही शेयर हो जाता है सर एज अ गेस्ट में ही।
Yes,
सर
sir,
हम प्रेजेंटेशन आप मेल पे लेके फिर हम यहाँ से शेयर कर देंगे
हाँ, ये कर सकते हैं। अगर
अगर
वहां
वहाँ
से
से
नहीं शेयर हो रहा है तो चेक कर लो एक बार।
जी
can you
जी
copy of presentation
Yes, sir. Yeah.
on same mail ID you have sent?
I've shared.
Is it visible to anyone? The
No.
slides.
नो सर
No,
That means it is not shared.
नो
Yes, sir.
Yes, sir. Need,
शैलेंद्र एक चीज कर सकते हैं सभी को एज अ प्रेजेंटेशन राइट्स आप दे सकते हैं वहाँ टीम में।
क्या मैंने एवरीवन किया हुआ है वहाँ पे?
हाँ हाँ अच्छा ठीक है
It
मैडम
is
को
already.
प्रेजेंटेशन अपनी स्लाइड शेयर करके चला देंगे।
Is it visible?
हाँ, अभी आ गया।
yes,
हाँ
sir.
Yes, sir. Now it is visible.
Please, ma'am. Hello, ma'am, you are muted. Please unmute yourself. Kalpana, ma'am. Hello.
पता है एक प्रॉब्लम हो सकती है अगर नेट स्लो होगा ना। यस यस, नाउ नाउ इट इज गॉट।
Ma'am, Kalpana ma'am. Hello. Hello.
इंटरनेट का इश्यू लग रहा है कि कनेक्टिविटी प्रॉपर बन नहीं पा रहा है, इसीलिए शेयर नहीं हो रहा था।
So shall we start?
Yes, yes, ma'am. We are waiting for that. Please go ahead.
Ma'am, PPT is visible to you?
No.
PPT is visible to you?
Actually, your system goes on mute mode. Maybe it is the issue with the internet. So just click once and wait because it takes time. Maybe you are clicking it twice, so it becomes again muted.
Ma'am, it is not audible. Hello?
सलेन अनम्यूट तो हम भी कर सकते हैं ना, आप अनम्यूट कर
नहीं हो
लीजिए।
पाता, अनम्यूट नहीं होता है, यहाँ से म्यूट हो जाता है, अनम्यूट नहीं होता है।
ओके।
एक्चुअली वो वहां पे ना सिस्टम में कुछ प्रॉब्लम होगी, तो दो क्या हो रहा है, जब भी अनम्यूट कर रहे हैं और लगता है कि अभी अनम्यूट नहीं हुआ, दोबारा क्लिक कर दे रहा हूँ तो म्यूट हो जा रहा होगा और वो उसको होल्ड कर ले रहा है सिस्टम को उसी पॉइंट पे। शैलेंद्र, एक बार आप बोल सकते हो कि मोबाइल से लॉग इन कर ले, क्योंकि अब तो प्रेजेंटेशन तो हम यहाँ से ही देंगे, तो अगर मोबाइल से हो जाता है तो वो भी बेटर हो सकता है, मोबाइल में हो सकता है सिग्नल बेटर हो एज ए गेस्ट ऑन द ब्राउजर।
I didn't catch that. Could you try again?
ऑनलाइन सिस्टम्स के ये कुछ हिकअप्स हैं जो बहुत ज्यादा परेशान कर देते हैं कभी कभी।
Hello, ma'am. Now it is okay.
Yes,
Hello.
it is visible now.
Ma'am, now it is okay. You are muted, ma'am. Unmute yourself. Hello.
Just wait, just wait.
Is also will be.
Can you see the
शैलेंद्र आप अपनी तरफ से stop presenting करो, then ma'am can share from there itself.
chat from my
हमने शेयर कर दिया है, मेरी तरफ से हो
अच्छा.
गया वो.
Okay, she has shared. Okay, so now she can open up that presentation screen.
Click on presentation PPT, so it will be visible.
Yeah, stop sharing, and in presentation mode, when you go, take the last one from my browser. There is one option when you say browse my computer. So from browse my computer, if you go to that file, then it will, yeah, now it will go. I think, yeah, voice is not there. Yes. Go to first slide. Yes, now slide is visible, but voice is not there. You can go to full screen mode and unmute yourself.
video is on.
Yes, now your voice, we got a bit of voice. You can speak again.
Hello,
Yeah, now it is audible.
now it is audible.
Yeah,
So I'll switch off the video.
yes. And make it full screen mode presentation from that lower corner. Yeah, from here, yes. Yes, now it is visible.
Okay, can I start?
Yes, ma'am, please.
Yes. So in today's discussion, we are going to discuss about battery management system for electric vehicles, which is a very well-known research area and upcoming areas also, where we now presently working for electric vehicles, wherever it is an electric charger or it is an motors. We are going to discuss how important is a battery management system and what are the techniques that can be adopted for improvising the management system or for particular batteries for electric vehicle systems. And the overview of the presentation goes in this way: introduction to electric vehicles and the type of EV and charging techniques. What is the modern configuration of EV? And what are the energy storage devices that are adopted? And why we need a battery management system and how to model the equivalent circuit of a battery for a lithium ion cells and how to estimate the values of a state of charge and the state of health and what are the techniques that are adopted. And to that, next we will be saying what are the cell balancing techniques. And we have going to discuss about the active cell balancing techniques also. And finally, the summary and the references. So we know that global e-mobility, the renewable energy source have become extremely popular in recent years due to increasing environmental concerns and the shortage of fossil fuels. So every field or application of the utilizing energy is switching to an alternative sources. So in the current world of automotive sector, electric vehicles have been found immense importance due to the same. So here we see that the benefits of electrical vehicles, and we all very well know. I'm just giving a brief idea about what is an electric vehicle and what are the advantages. It is energy efficient, it is environment friendly, and it has a zero part tailpipes, and that is zero emission, and the performance benefit is far better if we are providing a proper battery management system and if with advanced techniques where the performance benefits can be further improvised. And what are these vehicle types? And majorly with that plug-in hybrid and a battery powered, where we need a battery energy which is a heart of the device or a powerhouse of an electric vehicle. And we can see it in plug-in hybrid vehicle where we need a large battery than a regular sized hybrid vehicles. Hybrid and plug-in is for electric mode and where it can be used for a long range. And in case of a completely battery powered operated vehicle where we need a large batteries more than a plug-in hybrid and there is no requirement. In plug-in hybrid, we can operate the uh, car in both the ways. Either it can be for a battery operated and the both in IC engines also. But here, if you completely depend on the battery size, battery and so that large batteries are used here. And no gas engines, no tailpipe, and huge torque is required for starting of this motors. So here we can see that batteries are more important in these type of battery powered vehicles. So we are going to discuss about how to make a battery management system to power up the batteries for an electric vehicles. And PHEV plug-in hybrid and how it has been powered, whether we can use an household electricity or either it can be filled by using a gas station. And there are three models which are presently available in the market, which is a Chevy Volt and Honda City and Toyota. And what are the battery charging used? Battery we will be charging on the electricity and electricity which is use a plug and it use an internal combustion engines when the battery get depleted. That is an idea of why we are going for an plug-in hybrid vehicles. And basically, we know that what are the charging techniques, level 1, level 2, and a DC fast charging techniques. And if it is a level 1, 120 volt, it's a single phase which can, our household itself, we can charge the battery, which may take a few range, and it can be operated for to few kilowatts, 1.4 to 1.9 kilowatt. And the charging times and the range which can be obtained is only 3.3 to 5 miles of range per hour. And in case of AC level 2 chargers, and it is around 208 to 240 volt. It is the current is a magnitude of 12 to 80 amperes, and where we can increase the miles range here, and the charging load type will be of type 2, which is of 7 kilowatt or 19.2, 2.5 to 19.2 kilowatt. And now this the recent technology, the DC fast charging technique, where we want to charge the battery with a few minutes, where we don't want to wait for a long period of time to charge the battery, and we are trying to improve that where within a few minutes we can charge the battery and we can go for that riding. So we can see that the charging time it will take only 20 to 30 minutes to go for a DC fast charging techniques, which where we can have a research which is upcoming with that what are the DC fast charging techniques which are available at the recent technology, which are three-phase systems which is having a 90 kilowatt power, and we need a substation stations or electric stations where we can charge the batteries. So now recently the 3.3 kilowatt of a Chevy Volt to 100 kilowatt of Tesla model is presently available. And with this, we can see that if it is a charging station, we'll call the equipment to be an electric vehicle supply equipment, which is an EVSV. So with that modern EV configuration, so what is actually inside the electric vehicle? What are the components? So I have just put a block diagram of that, and you can see that four wheels and what is actually inside that. And it is an onboard charger, and we have a battery bank and an ultra capacitor. So both which has a backup, and there is a bidirectional DC-DC converter which is connected to a voltage source converter to an electric motor, and it is a bidirectional converter where from the battery it can be from either side, right? The way if it is for regenerative braking, from that also it can be charged from the battery and from onboard also. As a backup, we have an ultra capacitor back, or we can have a primary or the secondary as a backup for this. And we have two bidirectional converters and a voltage source converter for operating this electric vehicle motor, which is of a PMSM or it can be an PMBDC. So here that is another the main configuration, and the overall control will be taken care by the power controller here, which is provided. So which is another important concept how to control, because we have two sources and there is an onboard charger and we have a load electric motor load, and we need a dedicated power controller for operating this complete system. And we need an energy management system apart from this, where we have two sources. So how the power flow can be controlled, which if a battery is operated, then if it drains, then what is another option which has been kept, ultra capacitor. All these will be taken care by the energy management system, and which gives the state of the charge. So this management system will take that if what is the amount of SOC and how much miles it can be operated further. So all these options will be given by this energy management system, which is very important when you are driving the vehicle. If it is having a battery of only 40 or 50 percentage, how much how much distance I can reach with a specific time, right? So we are this one is a energy management systems, and we need a power flow controller, and these are the basic control schemes or converters. If you see that in between there is a converter and the charger and the motors, or the basic idea of what could be inside the LEV configuration. So when you're talking about the energy storage device, which is a main important for any operating electric vehicle, so the energy storage device, which are the batteries. So the electrical energy is typically obtained in case of batteries by the chemical energy conversion, stored in the batteries as batteries, or it can be the fuel cells concept. And among these available choices, either batteries or fuel cells, we can see that we need a portable energy source, and we don't need a high energy density where we can store the energy. If you see that all other resources which are available, we found that battery is the best option for making it provide an energy storage device for electric vehicles. And we can see that there are two types of batteries, which is a primary battery and a secondary batteries. And a primary battery, which is a non-rechargeable batteries, and a secondary battery where we go for a rechargeable concept of where it can be used. And where is this? Where we can accumulate this battery? So I just given pictorial view of where we can actually place the batteries inside. You can see that inside the car where it has been batteries and a battery management system, and where is main inverters which is connected with an onboard charger. The major type of rechargeable batteries. So we are going to talk about the rechargeable batteries, which are considered for electric or a hybrid vehicle. The first option is we can go for lead acid battery. We can't go for lead acid actually, which does not, where we want to increase the cycle life also. The second option might be the nickel metal hydride batteries. And the third one is a lithium ion. So we can see that out of these three, the battery chemical compositions, then lithium-ion battery technology is one of the most compromising over the other two types of batteries, as they perform well when it is used with an effective battery management system. So this lead acid battery where we use in for UPS and all, it does not have any battery management system. We can operate it only for 500 cycles. But if you have a dedicated where we can improvise the life of the batteries further for more than 3 years here with the proper battery management systems. And to further discuss about what are the chemical compositions, if I see with the starting from the conventional of lead acid, nickel cadmium, nickel metal hydride, and lithium ion, which is the last one is a lithium ion, where I'm comparing it with the conventional methods. And we have some of the parameters, if I compare it with that, I can see that lithium ion, which is having each cell voltage, it is of 2.4 to 3.8 volt when compared to lead acid battery where it can have only 2 volt. You can see that the size of that energy or the specific energy to be reduced, it will be very high. I can manage with, if I want to go for an 100 volt with a 2.4 volt, I can have very minimum cells when compared to a lead acid batteries. So here the battery lithium ions of each cell, which is of 2.4 to 3.8, and the energy density level, we can see that which is 600 plus, and the power density is of 5,000 when compared to the other battery compositions, chemical compositions. Here is important. So then we can see that the cycle life, which is of more than 2,000. So we want to compare cycle life. So here the cycle life, the mean is the complete charging to its 100% and discharging. So that we consider as one complete cycle, where we consider to be a number of cycles. This can be improved further more than 2000 if you provide a proper battery management. And the temperature range, if I check for the temperature range, it can be operated from -70 degrees. If the condition that it should operate, we have to sense the temperature. If we want to further increase that battery life, I have to put a proper temperature sensor to improve. So we can operate it from -30 to 70 degrees. And if I compare with all this one, and finally we can see that the robustness, we can see that everything, all other batteries are also operated, but if it is a lithium ion batteries, it need a dedicated battery management systems to estimate the different values and the parameters for a BMS. So we'll call it as the BMS here. So this is just about a comparison of how the lithium-ion batteries have more advantage when compared to the conventional chemical compositions of battery. And the recent one is the upcoming, which is a graphite. So everyone will be knowing that where we have more advantage when compared to the lithium-ion batteries, where some companies are overtaking to work on the research area, which where we have a graphite can be used as a better option for a lithium compared to the lithium ions. So whatever we have the comparative study that we have seen as a table, I've just listed out here, and here the conventional gel-based lead acid batteries uh, are used as an energy. It's a conventional method, and we can see the lead acid batteries have a very short lifetime, and where it needs a high recurring cost. That means every 2 years we have to replace with the new batteries if you want to improve the time. So lead acid batteries have a very shorter life span. And though lithium ion has many advantages when compared to that, here the very important is the overcharge and the under discharge, and also these two can happen with a high temperature range. It may deteriorate the life of the battery. So we have talking about only the advantage. Still it will be advantage provided if you operate within the range and also within the controlled range of temperature, we can improve the life of the battery. And more lithium ion batteries are costly when compared to lead acid, and if you keep on having a high recurring cost every year, and you can see that the cost of the battery is very high when compared to that other comp. If you only the cost of this will be high when you see a vehicle, you buy a vehicle, you can see that there will be separate cost for when you are going for a buying the batteries with the EVs. So lithium ion batteries are costly compared to lead acid, and failure of these batteries will lead to a high recurring cost. So to avoid this, a control mechanism is required to operate within the safe operating conditions. So I know the safe operating condition, how it should be operated, and I have to have a control of overcharging and under discharge. And what are the challenges that are faced in lithium batteries, and which is expensive to manufacture, and we need a protection is required for maintaining the voltage and current within the safe operating zone. And it is very sensitive to high temperatures and overheating, and it may causes not only, and it may have thermal effects also, and which may cause fire also. So we need a dedicated high temperature control, and sensitivity is also required when you operate in lithium ion batteries. And subject to aging effect, if it is placed as a shelf storage, it can have a 40 percentage of discharging. And the transport restrictions, where we have a regulatory, we cannot carry personally with some of the batteries. There is a restriction which does not apply to the personally carry the batteries. And when you talk about the safe operating area, how the voltage and current, if it is from minus 1.6 to 3.2, if it is a current where it is a voltage is ranging from in the y-axis, where I can operate the temperature within the zone, charging and discharging. And we can see that we have to keep the temperature within the zone where it is from -20 to 60 degrees. And this is a safe operating area for my when if I want to operate the batteries. And some of the basics before going to that, some of the concept of advanced levels. So I just thought of giving that some of the basics of a battery. The lithium ion cells which are connected in series, so you can see that the 3.6 volt battery, which is a NCR model, which is have a 3.6 of 3400 milliampere hour. So I can connect it in series of 3.6 to get a of 3400 milliampere hour, which is the voltage can be increased to a 14.4. And each cell of the battery, which is have a 3.4 ampere hour. A battery pack of 3.6 will have a 4S. So we'll call it as a 4S. So we connect 4 in series to produce a nominal voltage of 14.4. Right. So in comparison with a 6 cell lead acid battery, which has only 2 voltage per cell, we have to connect almost to get a 6 volt, will generate only 12 volt. So that is, we can see that the specific power density can be improvised when you are going for lithium ion batteries. And if you have a lithium ion cells connection in parallel, and where the number of it can be connected in parallel to increase the current rating, which is, we can see that if I connect it for 4, I can operate it for almost 13.6 ampere hour, where I can nominal voltage of this less packed remains to 3.6 volt. The voltage will remain the same, but the capacity is almost 4 times the original value. So this is an idea why we are connecting in series and parallel to making it and increasing the current and the voltage. You can see the total power is the sum of this voltage. So we need a 7.2 volt means we have to connect 2 in series, and all this both are connected in parallel. So it is a 4S 2S2P configuration. So it is a 4 cells which are connected in 2 series and 2 parallel, and which is operated at 3400 milliampere. If I connect these two series and parallel, I will be getting a voltage of 7.2 volt and 48.96 watt hour. So you can calculate what will be the watt hour, and the combination of this 8 cells will can produce about a 97.92. So why it is required to, if I want to have an increased watt hour, so we have to connect the number of series and parallel accordingly. And what is the hierarchy of EV batteries? So when we start from the monocell, and where we have to connect the number of cells to form a single cell, and it will be connected in a module, and from the module it will be a battery pack, and then complete systems where if you want to go 15 kilowatt, a number of battery packs will be connected in parallel. You can see that how it starts from the monocell cell module and a battery pack to a battery system. So these are the type of EVs which are present recently. So I'll just specifically go for some of this. So here you can see that if it is a 60 kilowatt hour, so 288 cells in 96S and 3P format. It will be connected 96 cells in series and 3 in parallel. So this is the format how they connect. And we can see that similarly the next configuration, which is an Mitsubishi, and which is of 16 kilowatt and 88 cells, which are connected 4 cells and module, and which are having a lithium ion batteries. So you can see that what are the vehicles which are connected in a lithium and how it is inside, how many number of cells can be connected in series or in parallel to increase the range. And we can see that what will be the charging time and the current, and if it is for 115 volt AC and for 230 volt AC, what will be the charging current, how much hours of time it will take to completely charge the battery. And similarly for a Toyota, we can see that it is a 4.4 kilowatt hour lithium ion, and it can have a range of 18 kilometers, where we can have the electric range is only 18 kilometers here. So these are some of the electric vehicle companies, and what are the battery capacity, and what are the charging plug type, and how much hours it may take to charge. So just a given introduction. So how that lithium ion batteries work actually? So we will very well know that it has an anode and a cathode, and we need a separator in between, and where you have a lithium ion cells will be moving from anode to cathode. So if it is a charging, we can see the lithium ion cell. During the charging process, all the lithium ion cells will be stored in a graphite electrode initially, Then in charge state, anode contains the high concentration of the lithium ion cells, while the cathode is a depleting region. And when it is a discharging, means it will be all the ions will be transferred from the anode to cathode. So this is a process. All the cells will be initially at one side, and only when if it is discharging, all the cells will be again moving to the another. So this will be the charging and the discharging. How it is accumulation of the charge, only the lithium ions will be attracted toward the other end. So with this battery definitions further, the batteries are specified by the three main characteristics. One is the chemistry, voltage, and the specific energy. So we have talked about the specific energy. Then chemistry, the most common batteries are lead acid, nickel, and lithium ion, and each system needs a designated charger. And when we talk about the voltage, the open circuit voltage, which is a fully charged battery, which is more than terminal voltage, which is 5 to 7% higher. And we have talked about the capacity. Capacity represents the specific energy, which is an ampere hour. So ampere, 1 ampere hour means for 1 ampere current for at 1 hour. So with that basic definition, so what is a battery SOC and the SOH parameters? So if you want to compare, what is the state of charge of the battery? So if I take a battery, if I talk about if it is a 70% capacity remaining, you can see the state of charge is 70%, and the depth of charge is 1 minus the state of charge. Will give the depth of discharge, a DOD. And the 30% will be the depth of discharge, right? So the battery capacity will can when it is initially it will be having a full 100%. So then when we talk about the state of health of the battery, what does it actually mean if it is a state of health? We can see that during the initial case, it will be having the complete 100% absolute state of charge and the relative state of charge. So how much percentage of charge is stored in the battery, if I take. And here you can see that over a period of time when you are charging and discharging, where that particular amount of percentage, you can say it is a battery is dead. Right? Almost if it is go for a 20%, if it is only a state of health, if I talk about only 80% means we can tell that battery is almost dead. So this 20% where you can see that the chemical composition or the ions, when there is a transfer of ions, more amount of the impedance will be accumulated across the anode and the cathode. Right? Then we will call it as it is the state of health of the battery. So which is important to define what is the state of health, how to estimate the state of health that is happening inside the battery. So initially when you buy, we have 100% of state of health, and during the over a period of charging and discharging, where we can say it has come down to 80%. And within this 80%, we have to charge the absolute and the relative. So what is one more parameter, which is a battery C rate, C rate of the battery. So here in this table, we can see that C rate and what is the time that is required to. So if it is a 1 C rate, so we need 1 hour time to charge the battery, and if it is a 0.5 C means, or it is C by 2, so the same battery will take 2 hours to charge. And if it is 0.2 C means it will take 5 hours, and now we are increasing the C rate to more. So we want to charge within a few minutes of 12 minutes means I have to increase the charge current, or we have to pump more amount of current inside the battery to increase it, where the C rate has to be increased to 5C, where the stresses on this device will be more. And we have, as a researcher, we have to take care of how to pump that 5C within 10 to 15 minutes to charge the battery with a specific, by keeping the temperature within the zone. So this is also one of the factors which is also considered when you are talking about any, or these are the terminologies which are used for our discussion here. So this is about the C rate and why we need a battery management system. So already we have discussed why we need to ensure the battery which is to be operated with an optimized value, and we have to avoid the damaging of the battery in a minimal, and the charging and discharging has to be monitored. And so all these parameters will come into effect. That's why we need a battery management system. And one is overcharging, charging current, and
voltage and the temperature. These are the main parameters which I need to take care of any battery. That's why we need a battery management system dedicated to that. Typical batteries which are having an EV configurations. This means 96 cells of 400 volt and 182 cells of 800 volt, where we have a typical capacity for a cylindrical battery of 4 ampere. So, yes. So the battery charges provides a single DC output voltage, which is either it can be a 400 volt to 800 volt, and we have to maintain required to monitor the and manage the battery pack to ensure the safety, reliability, and also we need to provide a cell voltage balancing, and we need a protection on the monitor, and in case if it is an any maloperation is reported, and it has to be provided with an alarm. So the main objectives, there is a wide if you talk about a battery management system, it is a wide. So we have taken very specific where we can actually control. Okay. So these are the main important things. One is a state of charge, state of health of the battery, and charge and discharge cycle optimization technique. And we have to control the current and voltage within the specific range. So that is also another important factor that has to be considered, adapting the performance within the temperature range. So nowadays we are taking the temperature also into account with providing a proper sensor. So these parameters, whenever I place a battery, I need to read that, and what are the techniques that will be provided to read these parameters. Okay, what are the methods that are to do it for to estimate the state of charge and the state of health of the battery. So then with that, one more is the cell balancing. So cell balancing is number of cells, as we have seen that it will be connected in series or in parallel. There may be some imbalance. So whenever the manufacturer, all the cells will not be in the same ideal case. So we have to provide a balancing between the cells where it can be further imposed. And this is a battery equivalent circuit. So we know that this is the top one, which is a charging characteristics of a battery, which is done for an 1C rate. So from 2.8 to 3.6 volt, it will take almost 400 seconds time to charge the battery. And for discharging characteristics also, whenever we want to study about the charging and discharging, we have to put the cell for these two characteristics, and we have to find out. And for discharging, we can go for all these 0.2 C, 0.3 C, 0.5, and 1.0 C. All these T rates, we can see the terminal characteristics of the battery. So we can see that it has a dynamic resistive model. It is a somewhat, if I want to model the battery, what will be the characteristics? So first I have to study about the characteristics. We can see that there will be some drop in the voltage. So we can see that some resistance is connected in series with the cell voltage, open circuit voltage, so that if it is a charging and discharging, there will be some drop in the voltage. So we can see that it is a non-dynamical resistive model where the discharge and charge test has been conducted for each cell by using the HPPF test, and we have to estimate that and find that the basic model is a resistive model. And the next one is a dynamic modeling, where if I provide a short current or current, and how that it will behave. What will be the voltage and current? If I see that there will be charging and discharging current, there will be charging and the discharging current here, and how that voltage and current, you can see that there will be a short transient that is appearing here, both the sides when it is charging and discharging. So I can assume that there is some transient or some RNC component are present in the battery. Right. So after going for a repeated test and all, we found that there is some transient is appearing where we have some component of RNC which has to be done when you are going for a complete mathematical modeling. Okay. So from these two analysis, where we have a dynamic modeling and a non-dynamic modeling, which is having only resistance, and also we need to make it as a dynamic Thevenin model. So this is the basic model where we have. So the first model where we have seen that it have a slight drooping characteristics, right? So with an open circuit voltage and a battery voltage, we can see terminal voltage, we can see it. So we can estimate that there will be some resistance connected. With the further exact modeling, we can see that there will be two tank circuit which are connected, because of dynamic modeling, we can see that if I impose some current into that battery, it will be having some transient characteristics where R and C are connected in parallel. And we can increase, if we want to go for a more exact modeling of that, we can make it more exact model by connecting it number of two. Either it can be a 2RC or a 3RC network where you can to estimate the values of R and C exactly. What will be the value of RS, what will be the value of RP, CP, and other parameters can be estimated from the whatever the data we provide. And how to estimate the estimation techniques. So there are many algorithms which is used to measure the SOC. And one is the online method. We want to go for an online method. Online and offline method is battery will be always all running, and we want to estimate what will be the state of charge always. And is an offline means you disconnect the battery and measure what will be the state of health of the battery, and where you have to remove it, disconnect from the battery from the setup, and we have to go for. So that if you do want to disconnect the battery, and you can go for an impedance spectroscopy where there will be some impedance over a period of time. There will be some accumulation of charges in the between anode and cathode, and where it has an impedance. With that measuring device, we can measure that. So if it is an online method where we can go for there are methods. This basic method is the one is a Coulomb counting method. So it is the green one which is shown as an online method, and the red one are the offline methods. So the Coulomb counting method where the accumulation of charges over a period of time, how it can be estimated. So that one is a conventional method of one is the Coulomb counting method, and the ampere hour method almost with a slight difference. That both the techniques are almost the same. And the open circuit voltage method and the impedance measure, which is an offline characteristics where it can be measured. And apart from that, the recent methodologies where we can go for a machine learning based algorithms with a neural network and support vector machine, which is also another which one another recent methods where you can really work on improvising the methods, and the Kalman filtering method and predictive control methods. And these methods are adopted for more giving accuracy and a true value very near to the original value. Right? We are estimating the value which is very near to the true value. So the advanced method is state space model estimation using the Kalman filtering. So we have done for the Kalman filtering, and we have compared that with the conventional method, and how far our algorithm is very close to our the conventional method true value. So if you provide a 2% variation also, it will increase the efficiency of the battery. So with this discussion of this battery, and we have modeled, so you can see that there's a complete modeling equivalent circuit of them where it is considered for our battery characteristics. There I have shown that dynamic and the non-dynamic model, the resistive model. So we can see that we have a resistance, and we have also connected the RSD, which is and also the capacity, that is internal capacity of the battery, for further making it as an exact model. And we are taking it to be a complete equivalent circuit. We have modeled that battery with that characteristics, and we can estimate the value of LUOC and RL. All these parameters can be estimated. And if I want to estimate the terminal voltage, plus or minus will be considered when it is charging or discharging parameters. So we have worked by considering this state of this equivalent circuit. And this is a conventional method of Coulomb counting. What is a formula that is used to measure that conventional state of charge? So you can see that which is the initial method, SOC characteristics for the initial value, plus or minus we will decide about whether it is for charging or for discharging. And we are battery current with a usable capacity over a period of time. So this is how each and every time it will be updated. The current will be integrated over a period of time to study the temperature. And these characteristics which shows a lithium ion with when it is open circuit voltage, and also the discharging characteristics which is almost considered to be a linear range. And we can see that all these parameters VL, VC, ES and V series. So this is the voltages that we have measured across that series voltage. So this is the series voltage. What will be the series voltage? VS and VL. And this has been shown here. You can see that that series characteristics which has a dynamic characteristics when we measure the individual voltage of VL, VS and VCS with respect to the state of charge. And what is this Coulomb counting method based estimation? So we can from that Coulomb counting method we can estimate the state of health of the battery. Once I find out what will be the state of charge, and I also estimate the values of SOH. So the formula which is related to that QI by Q naught, and QI is a discharge capacity of the battery within any cycle after a period of time, what will be the cycle, and the initial value divided by the initial value when I buy the battery for a new one, what will be that initial value which is provided in the data sheet, and from that I can estimate what will be the state of health. So this will be the discharge characteristics after 400 cycles, completely discharged battery. You can see that the state of charge of the battery when it is SOC, in terms of SOC. This is VT is a terminal voltage and the state of charge of the battery. And one of the issue here, if I go for the conventional method of estimating with that Coulomb counting, if I want to estimate the state of health of the battery, and over a period of time, if I go for an discharge inaccurate, it gives an inaccurate results. If it gives an inaccurate results when it terminates in between, suppose if it midway, if it is terminated, again you are charging. You can see that this blue line which shows it is charging, and it is not completely discharged. Then again discharging, and again I'm providing the charging, and it is increasing, right? So if I do with this estimation technique, which can come to a value which is an inaccuracy of, it will give a state of health is which is only 59.7%, it will give an inaccurate value if it is a mid of the terminated, right? But it is not actually so. If you go for an 80% of state of health of itself, it is battery is almost it. But whatever this estimation technique which is shows an the conventional method which shows an inaccurate value. So we have tried to what are the possibilities of estimate battery, and if it is a midway, if it is terminated, and if you are going for a variation in discharging current, well, initially it will be for from 0.3 C. If I'm estimating for 0.3 C rate, then I'm discharging for 0.5 C, then I'm discharging for a higher value of 1 C. So you can see that discharge rate is different. Where we usually operate in an electric vehicle, where if you want to go for an increased speed, the charge of the battery will have a it will be more. Depending upon the speed, we can see that what will be the charge current, the discharging current. So if I go for a multiple discharging rate, what will be the characteristics? And how accurate is my state of health is giving, whatever the values, right? And if I go for a discharge characteristic of a lithium with a different charge rate, what will be, you can see that the characteristics will differ if I go for a discharge characteristics of a different C rate of 1C, 0.5, 0.3 and 1C. So we try to modify the Coulomb counting where by considering I have a complete discharging, I have a complete discharging in midway also if I do, whether it can give any accuracy method and what modification it can be done with respect to the conventional method, and we slightly try to mod instead of taking that denominator of Q naught, which is the initial value, we try to estimate for over a period of time from T1 to Tn. Then we can find out the charge from T0 to T1, and we have changed the algorithm, modified the algorithm in such a way that where we can get a more accurate value of estimation, right? By considering also SOC into our account, how we can take the Q naught value, and that value can be used to find out the accurate value of SOH. And we have done some of the simulation results which we tested our algorithm for a complete discharge with a different temperature. So this is 35 degrees and also for 40 degrees with a different temperature characteristics for 450 cycles and also 1020 cycles. So every day we had in our lab with the two batteries where we daily charge and discharge so that we can have a cycle variation, and which can be operated for different cycles and also for different temperature effect heating. And the case 2 where we have done it is for a partial discharge case. In between, if it is a midway, what will be the characteristics? And you can see that our estimation technique, so it's give most or give by using this method of by once we calculate SOC and from that we calculate SOH, and we can see that it almost gives a better results when compared to the first two cases, which is 90.875 and 84, which is a state of health of the battery we are reading. And the partial discharge test, where you want to terminate at the mid of this battery when it is a 450 cycles aged battery. So 450 cycles it is charged and discharged. And if I mid of that, if it terminate, what will be the state of health? Further, how long? Why you want to go for the state of health is how long the battery can be operated further. I need that estimations. Okay. So whether another 6 months, whether I have to replace that battery. When it reaches as 91.97 means I can see that okay, the another 1 or 2 years after that I need to replace the battery. So this is very important when you go for where we want to study about the state of health, for how long we can go for estimate use that battery for how much period, whether how we can improvise that life of the battery further by taking the temperature effect into consideration. And we found that with these characteristics, whatever the modified algorithm, where we can find an accurate method of finding the SOH. And we have tested the same with multiple discharge rate for Q1, Q1 of 1 ampere hour and Q2 of 0.44 ampere hour and Q3 of 0.25. And this characteristics which shows that where the Coulomb counting characteristics which is integrated, right? The formula which is an integration which shows that current accumulation of the charges over a period of time, how we are estimating the value. And these are the some few results which represents for Coulomb counting characteristic for 1C rate and also for different charging rate. So this is for the multiple discharge rate. We have been tested in for setup. And this is one method where I can go for an online estimation where we are estimating the SOC and also SOH with a modified, and how accurate is our result when compared to that conventional method has been discussed. And the DC resistance based SOH, if I want to measure the DC resistance, where in some offline method we have to remove the battery and make it in a connected to an impedance spectroscopy, and we have to do, but you can measure the DC resistance online also. So we have done some modification in that SOH estimation where it is equal to the estimated value of resistance, right? Impedance of the battery at the end of the life. So what will be that at present? What will be the resistance and over a period when it is a battery at the ith cycle and when it is new? When I carry out all these values, I can find out what will be the SOH. And here the one of this, what is a how we conduct this experiment is we are going to give a pulsating discharge current, and how long it will be that voltage will be decreased, and delta V. Basically delta V by delta I can estimate what will be the resistance. What will be the resistance, series resistance drop, and the transient response. If I can find it from these two, I can find out from what will be the resistance. I can estimate from that resistance, I can find out what will be the aging of the battery. Can be easily studied. And with this is the characteristics where we study about the Coulomb counting based SOH method. And with this a setup that we used, where we used a converter to charge and discharge the battery, and we used a D-space controller uh, to verify our algorithm. We have used a controller here, and we have results for SOH estimation. We can see that in this with the colored definition here, the cycle 1 and cycle which is of 500 cycles. As a number of cycle increases, you can see that the black one which shows that where the resistance is more over a period of time, we can see the transient period. We have to give a pulsating, and from that we can estimate that over a period of cycle how that depth it has been increased if I go for this type of characteristic study, that another method to find out the SOH by measuring only the DC resistance and the cycle number, the number of cycles, and what is the DC resistance and the state of health of the battery. So you can see that when it is a cycle number one, the one cycle, and which is a new one, right? So which is our state of health of 100%. That means it is a new battery. And if I go for 100, 500 cycles number, that is 500 charge and discharge, it is almost 97.07. And almost you can see if it is more than 2500 cycles, 2000 cycles, you can see it is almost 77.82. That is, battery is almost dead condition, where we need to replace a new battery, which is estimated. So these are the methods to find out the SOC and the SOH methods for finding these parameters. And the same we have tested in the lab with the characteristics, and we found we are estimating the delta V, which is of 360 millivolt. And if it is for a few aged cycle battery, we are estimating it for a delta V, which is of 420 millivolt here. So the terminal voltage we are estimating, and also the charging current, discharging current. And we did whatever this proposed method was done by Sai Krishna, my student, where we have filed on patent also based on this SOH, the modified Coulomb counting. And this is a setup which has been shown for conducting the battery. So that one converter and with a D-space controller, we have tried to verify and that whatever the control scheme that we have proposed, which has been estimated by using a D-space controller. And coming to the, so far we have discussed about the SOC and SOH estimation, and now we will discuss about the cell balancing. So what are the methods? So this is also an important aspect of studying the cell balancing. So this is also one of the upcoming area where which is really required to improvise the health of the battery further. What are the methods that are adopted for making the cell balancing techniques, and what are the converters that can be used to charge and discharge the battery? So we can see that for this cell balancing. So for cell balancing is a method of equalizing the voltages throughout all the battery packs. As we have discussed earlier, we have a set of batteries which can be connected in series and in parallel. So which are connected in series and parallel, where SOC, either we can balance the battery with the voltage and with respect to SOC, state of charge. So there are two standard categories. One is a passive method and another one is an active method. And in passive method, where we connect only some resistance across the batteries, where the excess of energy can be transferred to that, where we are dissipated through the resistors. That is a passive method. So we are not properly utilizing, some of the energy can be wasted, right? So here next, if I go for a switched shunt capacitor, where we can use active switches into the technique, where if it is an overcharged battery, whatever that can be transferred to the which are having a low voltage. So we are trying to balance among the cells. So that is different techniques which are adopted to operate for balancing the cells by using active balancing technique. So in this method of active balancing, either it can be a capacitive or an inductive, or with isolation or without isolation. So mainly this method maximizes the battery's available power and also more effective when compared to balancing. So where the excess energy, instead of dissipating, we are trying to balance among the cells. In active balancing, mainly it can be categorized depending upon the switched energy storage device or the converters, DC-DC converter based topology and the transformer based. topologies. So these are the basic topologies, and there are a few converters based on that. How I want to charge the battery from where to where, that is from target cell to source to target. So source means where it has a higher voltage or the higher state of charge. So from that, where I want to transfer the voltage. So depending upon that, it can have either I can go for cell to cell or from cell to pack, cell to module and then to the pack. Okay. So it has a configuration, say either it can go from some cell to pack, and if it is from cell to pack and again to cell. So all these possibilities of configuration is possible, and from pack to cell is also there. So here, if it is a cell to cell where we have a very limited configurations, which is our single switched capacitors and double tiered switching chip converters and buck boost converters can be used, a resonant converter. But if I go for the cell to pack where we need a modularized switching transformers with the multiple windings, and if it is cell to pack means where we need a bidirectional multiple transformers, and if it is a pack to cell is almost very similar to cell to pack to cell. So this configuration mainly we can adopt for this also. So these are the different schemes that are available to have a how to balance the cell among that, where we can go for different configurations. Okay. So these are from the literature we can see that we have reviewed that these are the basic topologies which are available for active balancing. So coming to this capacitor-based balancing circuits, and the mainly which is a single switched capacitor. So you can have a one single switch capacitor, and you can see these are the batteries B1, B2, B3, and B4. And with the one capacitor charged, either we can go for single switched, and by operating this switches with a proper controller, we can charge the balance the battery voltage B1 among the B1, B2, and B3. And if it is a chain structured switched capacitor, we can have a chain of structures where among each battery we have each cell to charge the battery, whether it can be overcharged or deep discharge, or if it is a more cell or more voltage is there, again the capacitor will be charged, and if it is a low voltage means it will be transfer of charges from between the capacitor and the battery. And the third configuration is a MC balancing circuit. It is a multiple capacitors which are connected, where we are in modular configuration. Basically, it is a modular configuration where we can accumulate a number of charges because batteries which are connected in series or in parallel methods. And if it is a converter based, so there are few techniques which I explained. The previous one is a capacitor based, and if I go for a converter based balancing method, we can see that converter based, a buck boost converter based balancing method, where we have four cells. So these are each cells which is of NCR configurations, where we have a B1 battery for each cells, four cells for example, if it is connected, and by the configuration of a buck boost converter, how to charge, make it an equal charge among that. Suppose if it is a 3.2 and another one is having a 3.7 volt, how we can accumulate the, make it as a balanced cell among all the three. So this is one configuration which is given for a buck boost converter. And the second one is a resonant converter. We are trying to modify that with the resonance. So we can see that it is more or less the same with the buck boost converter. Sorry, with the balancing resonant converter, where we want to improvise the efficiency of the system and by using ZVS and ZCS methods. And this one is the third one is a centralized balancing circuit. And in that centralized balancing method, you can see that the center one, it will be the charged, and from this is the source cell, and this will be the B1, B2, and B3, 4, and 5 will be the target cells. So accordingly, we will be discharging depending upon we will be sensing the voltages. From that, we will be charging and discharging to the other cells. And these are the transformer based, which are isolated configurations. basic configurations which are available. Either it is switched multiple windings, where we can see that each battery is connected to a multiple winding transformers here. And the second one is a multi-winding transformer based, where we have a common charger, either a current or a voltage, and we are charging it to the each cell, each batteries, how we are charging. So these are the methods. So one of my student, he is working on the converter based. So we have chosen the converter based of active buck boost balancing circuit, and so this is what I have shown the conventional method. In this conventional method, we have modified it to some extent, so that how we can improve the efficiency of the system. So here I have shown only the conventional method. So here this buck boost cell balancing method, we have taken the 3 switches, and if it is a 1 stage and if it is 2 stage. So what is the difference here? 1 stage and 2 stages. In case of a 2 stage, we have module balancing first initially, then from the module it goes to the cell. So each cell is of, suppose if it is a 3.5 volt, so almost 10.5 volt will be the total voltage. So first we will be, first initial stage is module will be balanced, and from that each module, then each cells will be, whichever the module, C1, C2, C3, we can see it is under module 1, and C4, 5 and 6 under module 2. So whatever the complete charge will be first initially balancing the module, and then we balance the each cell under the each module. So this, whichever inside here, we will call it as a cell equalizer. So we need a switch S1, S2, 3, 4 and 5, or will be for the cell equalization. So we have to operate the switches accordingly to balance the cell among the C1, C2 and C3, and these module switches SM1 and SM2 will be operated. So depending upon if which module will be higher or lower, or the target module or the source module. Source module will be having the higher module, which we consider higher voltage when compared to that module 2, and we will be transferring initially balancing first the 2 modules, and similarly if I go for a complete pack, first pack will be balanced and then comes the module, and then we are balancing the C1 inside the cells. That is a hierarchy that usually will be done. So here that is a 2-stage cell equalization method that is adopted. And so in this method, we can see that how we transfer the charge to the nearest cell. If suppose C1 is greater than C2 and C3. I take an example of if C1 is greater than C2 and C3. So we will be operating the switches. So whatever the charge, highest charge will be, make all these voltages will be balanced, which will take consider 3.4 for 5 for each cell, and accordingly it will be done. And we have individual voltage sensor has to be connected. We need an individual voltage sensor, and if that voltage, a specific cell, if it is goes more than that, then we have to operate the all the switching signals will be generated, which should be operated accordingly. So for this modules, we can study almost the 4 cases. So when it can be a cell to cell with the nearest cell, or unit to unit, and with us one cell to the nearest cell. So there are different modes that can be operated. So accordingly, we can modify the structure of the configurations to an extent. So we have almost considered the 6 cases of which can be operated only to the nearest cell. So if the charge, if it is C1, if C2 is greater than C1 and C3, so how it will be charged? Because it is not, C1 and C3 is not very near to that. So what we will do is, first we will transfer the charge to C3, which will come to the any one of the modes, mode 1, mode 2, mode 3 and 4. Then we will be transferring the charges to the nearest cell. So we can categorize how these self discharging can be done with possible modes of operation. So we are actually working on this cell balancing with that converter topology. And further we have modified with that conventional, which I have not discussed here because he is working on that research actually. So just to give an idea about how we can have where we can actually start do our research in this cell balancing methods. Okay. So with that, we have started with some hardware setup where we can see that with the two modules. So separately, I've shown that this is module 1 and module 2. So we have done made a configuration by connecting three cells, which is of NCR. Then we have module 2, and first we initially balanced the two modules. Then we finally balanced all the three cells, so almost at a 6. So we have just given examples of if it is a 6 cell, how it can be done, right? So 12. So each cell is of 3 point means almost a 12. So 12 multiplied. Either it can be a 48-volt battery, and we can have a multiplication factor of that. Right. So we have done a small experimental setup which is conducted. All this PWM will be generated from my FPGA board, and we have gone for the two-stage algorithm with a slight modification in the converter configurations as I discussed, and we have tested whatever that proposed modified controller and also with that converter, both configurations, and we have done with few experimental results also. And this is how actually how far our proposed method and how the cell balancing is achieved. And we can see here the first one is where with that experimental results, we can see that this is C1, C2, and this is C3. We can see that C1 is more than C2 and C3. And over a period of time, we can see that how the balancing is achieved after almost 700 seconds it will take. So you can see that this mode is more than C1 is greater than C2 and C3. So how the balancing operating can be carried out, and over a period of 700 seconds we have achieved. But this is a method which is a conventional method, but we have tried to make it very less than 420 seconds. So with our modified configuration, we are able to achieve the balancing speed very less when compared to the conventional method of charging. And the second one is where B1 is V3 is greater than. So this V3, cell 3 is more than V2 and V3. So what will be the condition? So how much time it will take? So we have tested it with that. Within almost 750 seconds, we can see that we can charge the cell and almost all the three cells. So this is C1, C2, C3, where the difference of color has been shown here. And the third waveforms which show the it is a combination of both the cell and also the module. So first we are initially balancing, as you can see that blue and this light blue one, where module 1 and this is for module 2, and where we are initially balancing the module, and further inside what are the under each module how many cells are that balanced. So we can see that in that method almost less than 600 seconds we are able to achieve the balancing. And after we can see that this period, this is the second period, this is the period A where we are achieving the module balancing, and B is the period where we are achieving the cell balancing. So we are able to get it for one less than some 50 seconds almost with that. So these results which I've shown, it is a conventional method, and whatever I told that in modified method where we are able to work on the module and also with the cell balancing, we are able to achieve that almost less than 450 seconds with a high balancing speed and efficiency with whatever the buck boost converter topology, the converter schemes, what we have explained, the capacitor method is available, transformer method, or if it is a converter based method. So now we are doing it for module, and further we are going to extend it for our pack, the complete pack. If I use it for a battery a pack, what will be the configuration that can be used for taking it? And this is how the third one, which shows that module 1 and module. So to summarize, so what we have gone through that battery cell balancing methods. What are the We have discussed about how to arrive a battery circuit with equivalent circuit. How we are designing the equivalent circuit by testing, conducting the different test on the each cell, not the complete battery. We have conducted that for each cell. From the charging and discharging characteristics, we have obtained it for the dynamic model and the non-dynamic model, and we have arrived with a complete equivalent circuit with the parameters, which is very important when we discuss. When we go for any study of this battery, basically we have to understand what is the modeling of that battery, then only we can further go for extending our characteristics. So whatever that cell balancing method that we have discussed, we have taken only the voltage parameter. On the same, we can estimate it for SOC characteristic also. So if you want to study about the SOC characteristic also, again I need for an equivalent circuit for each cell, how to model. Right. And I need to propose, we have to find out a controller, the control scheme that can be adopted to find out really what will be the equivalent circuit. So that is how it is important to know about the equivalent circuit of the battery. And the second one is we have studied what are the two methods has been discussed for state of health of the battery. And one method is the modification of the conventional Coulomb counting method to estimate initially the state of charge and thereby estimating the state of health of the battery. And the second method, this first method, which is an online method, so prefer online method of estimating, and the second method which estimates the SOH by measuring the DC resistance also. So we have done it for this estimation for an advanced UKF method, uh, uncentered Kalman filtering method. So we have done for our extended, still we are working on the Kalman filtering, extended Kalman filtering for estimating the SOH parameters. And we have discussed about these two methods in case of SOH and cell balancing. So the another important topic what we have discussed is cell balancing techniques and what are the types of cell balancing technique and how we can start working on that basic idea behind that. What type of technique I can adopt, or if I go for a research which I can really work on a cell balancing, what exactly I can choose a configuration. So different methods and capacitor, different methods have been discussed, and finally we have tested what we are actually doing in our laboratory with a buck boost converter topology, which is a modified method of the conventional buck boost converter to balancing the batteries cells. So, so these are the reference. So we can, these are the two topics where we can really work on the research. And one is estimation techniques, also the cell balancing techniques. And another one is in that method, we can work by making the temperature also into taking into account. So further, if I want to further improve that research or improvise means we can go for the temperature sensing where we can extend the life of the battery. So where the first two methods we have discussed about how to estimate the battery, we have estimated. But is it really possible to extend the life of the battery? How to do that? So the one method is you have to go for temperature effect consideration into account when you are charging and discharging battery. And how when you consider the temperature also into account, how the equivalent circuit is modified. The equivalent circuit will be considered in terms of temperature variation. Right? So you can modify this equivalent circuit. If I go for making the temperature into account, there will be a modification in the battery equivalent circuit. And further, we can modify the parameters related to that estimation of SOH with respect to that temperature also. So in few industries now they are discussing about how we to manage with the temperature effect. These are the conventional methods. How we to consider these methods by taking how to improvise the life of the battery. Right. And similarly, the cell balancing technique, whatever we have discussed, the same with that temperature can also be taken into account when you estimate the SOC. So the first we have to worked on this technique, and then what are the converters that we are adopting, and the same methods we are adopting for whatever these estimation methods we are considering it for our cell balancing techniques. So these are the main references. Thank you for listening. Hello.
Yeah, thank you, ma'am, for your
Thank you, ma'am.
yeah
Thank you.
introduction to this topic and going into the details. Now we have open session for the questions. If anyone is having any kind of question, please ask.
Yes, sir. Hello, ma'am. Good evening. Hello.
Yes, good evening. I think you can hear.
Yes, ma'am. Yes, I can hear you, ma'am. Yes, ma'am. Actually, you were discussing about the cell balancing, right? So, means like how you are deciding like which cell to balance or like which is overcharge or undercharge, like based on the SOC of that particular cell, or you're taking the OCV, means open circuit voltage of that particular cell, and you're like deciding like which cell to be balanced or not.
Yes, actually, this is a right question because how we are sensing the voltage, which voltage we are, how to know that which cell is more. So we have to provide each sensors for each battery, and so there are three different cases. Either battery can be balanced in charging mode, and also during discharging mode, and also in standalone mode. So there are three modes where it can be you can balance the battery when it is charging and discharging, and in the standalone condition also we can operate. So we have tested initially for open circuit. You can see that these results which shows only for we have balanced with the initial cell voltage, open circuit voltage only we have tested. And if I modify, if I want to estimate the state of charge, okay, so whatever the control methods that we have done for that SOC, the same we are trying to implement by using SOC. But what we consider that SOC will be more accurate when compared to the cell voltage, and now we have done only for the cell voltage. And the second objective we are considering also the SOC also, one of the parameter that will be more accurate when compared to OC voltage.
Yes, ma'am. As you told, SOC will be more accurate. And
Yes.
one more question for me is like, as you told, means you are taking module wise, because like you are grouping, like in order to tell in more technical way, like grouping two or three cells in a module, and you are like balancing first in between the module, then you are like balancing that module with the pack. Is my understanding right? Is
Yes,
that the way like
exactly.
you're
Yes,
doing?
exactly. Correct.
Yes.
So
Yes.
first initially it is a two stage. So first we will go for only the model balancing. Then we'll go for cells which are connected to each modules. So we'll be going
Oh,
for module.
oh,
So you give to give a comparison how far the each module will take a time to balance, and further if a cell is considered, how far it will that cell will consider time it will take to balance. And
okay,
now
okay,
apart from this, because all these modules will be again connected in pack, right? The
mm,
series and parallel. So we have to go for pack how it can be balanced first. Then comes this module and then each cells. So
okay,
we are also working on for complete the battery pack of 48 volt where we have a large value, right? So how that can be achieved for by taking any converter topology or with our converter topology, how it can be done for a pack, battery pack.
okay, okay. Yes, ma'am. Thank you.
Thank you.
Any other participant?
Ma'am, good evening, ma'am.
Yes, good evening.
Yeah.
In initial slide, you have discussed this applications of different types of batteries, in which it was their memory effect. Means what it is, and is it related to SOH?
No, it is not related to SOH or SOC. Memory effect is if it is what will be the charge and discharge. It is not related to SOC and SOH. It is a different technique where what will be the effect of that if it is a self charge, self discharge, right?
Ma'am, what memory effect? I don't understand.
So memory effect is suppose if I charge and discharge the battery for a particular over a period of time. Okay, so over a period of time, how I charge and discharge. So how that memory effect will come into effect in case if I am working for over a period of time, right? So how that effect will be considered? One second. So that memory effect can be that is not related. If you want me, I can just have a just you can send a query. I can reply for that. Okay.
Yes, ma'am. Thank you.
Anyone else? Okay, I hope there are no more questions. Ma'am, I have one just a small doubt.
Yes, sir.
Suppose we have a battery at initial stage, how do we estimate the state of charge first time? Have you encountered such thing or have you done this thing anytime? Because we are not aware of the state of charge. So first time how we get the state of charge for any battery? That is a
Okay, so your if it is a new cell or
yeah,
a new battery, how to estimate the SOC?
yeah.
So either you have to make that battery either put it in charging and discharging characteristics, and we can estimate the current, what over a period of current, what will be the over a period of how the charging and discharging can be done. So
Okay,
with that
that means we have to
HV
estimate it. Initially, we have to estimate, and then
yes,
later on, we can continuously
continue.
get into.
Yes.
Okay, okay. Thank you. Thank you. Any other question from any other participant? So I think everybody is done. Thank you very much, ma'am, for sparing the time because it's a hectic schedule. You were busy in some other work also, and you have accepted our invitation to be the expert for this faculty development program. And this topic was actually very much needed because all other experts are talking about the converters, the charging schemes, but battery management was very much needed. So really your contribution was great to this FTP and well explained in different domains. Hope that all the participants have got uh, some takeaway from all these presentations. And if there is any query, you can put it, you
Yes.
can
Yeah.
send us also.
One of the
So
queries, which is a memory
yeah,
effect, more explanation I can give. You can send
yeah,
ask.
you can just
I can
send, you
share
can
my
send.
mail ID and I can answer through that.
Yeah, because next week we'll be having this physical mode for all the participants, and we'll be discussing many other topics. So by the time, if you just reply, I'll convey to all the participants. So once again, thank you very much, ma'am.
From my side, I thank all the participants and also the team coordinators for inviting me for this event. And I'll be happy to again join in any of the moments in the future endeavors also. Thank you.
Thank you, madam. Thank you so much.
Yes, thank you so much. And I think after a long time, I'm meeting Sir also.
Yeah.
Yes,
It was
yes, yeah. Actually, 2 years of Corona, and maybe after completing your PhD, you have shifted on to NIT Surathkal. So we had not had interaction anytime.
So
Hopefully,
actually,
we'll have, because I may be visiting to Kannur sometimes in this year end. So I'll try if we can have some get together there itself.
yes, sure, sir.
Yeah,
Whenever-
still one a candidate from Kannur you are taking as a research scholar?
yes, JP is Mrs. JP.
Yeah,
She is
yes,
one of
yes.
my student.
Okay.
She is
Yeah,
working. So I have a regular interaction with JP sir, and we have contact daily, not daily, occasionally. If there is any conference from the Kannur and he invites, and if we have any conference and we invite him as a special invitee, and it
yeah.
happens.
How far it is from your institute?
From here, it is 100 kilometers from here to
Okay,
get
so
down at Kannur. It is 2 hours journey from here.
yeah,
It's
so
not
it's
so. I make sure that within 100 kilometers I can move.
yeah, yeah, that's good. Okay, so next time if we be there, then definitely we can have some kind of interaction. Okay,
Yes, sir,
thank you.
sure.
I actually I had seen your hardware setup, so I'm also interested to see those things, because it is very interesting to have battery management in the laboratory, because it's
I
not very
think
much easy.
Shailendra sir, he might be knowing Sai Krishna.
yes, yes, ma'am. We have
He worked. He came to IIT Delhi, and the one of the PV methods and all. He worked with Shailendra sir, and
Okay,
he
okay,
also we have a publication with him also. One
okay.
paper he got it from, and he stayed there for and he supported. Thank you for that.
yeah. Thank you,
And
madam. Thank you. That's guy has published 2 transaction papers, so that was great. I mean, only in MPPT as well as in battery management.
yes, yes, yes. Because of your support and Professor Beam Singh support, he could able to do that. And actually, he was he is the first student where he put that battery management, and he diverted my topic to battery management systems. And
Yes,
you very well know, sir, I was in power quality.
yes, you are completely
And
in power quality with
uh,
multipulse.
yes, now
Yeah.
these students have diverted my topic to this area of battery and EV and that charging
It's a good
techniques.
diversion, because nowadays EV is very much hot cake for all the researchers. So that is good diversion.
Yeah. So, yeah.
Okay, thank you,
Because of
ma'am.
my students, I was able to achieve that.
Sure.
Okay. Thank you, sir. Thanks for inviting
Convey
me again.
my regards to Ramesh sir also.
Yeah, sure, sir. Actually, I told your name, and he could not able to recognize. I told him.
Just tell him badminton partner with Tandon sir. He
Oh,
knows that.
oh, okay. Yeah. Even my daughters, they remember you. And
Okay,
okay, sir. We'll
okay, ma'am.
discuss later.
Thank you very much.
Thank you, sir. Thank you, Dr.
Okay,
Shailendra.
Thank you,
take
madam.
care.
Thank you.
Bye. Okay.
And thank you, participants. Thank you so much.
Thank
Okay,
you,
sir.
ma'am.
We'll make a leave. Thank you.
Okay, all the participants, please stay connected. We'll be having a little bit of discussion after this session. So as discussed earlier, I'll just go through one of the presentations.